I want to start today by reminding you where we ended up, that the force between any two objects is based on the mass of those two objects, the separation distance between those two objects, and a constant of universal gravitation that we believe is the same everywhere in the universe. This constant of universal gravitation, 6.67 times 10 to the negative 11th newtons meter squared per kilogram squared. The first thing I want to talk about when it comes to Kepler is Kepler said that the planets orbit the sun. Now, I'm going to use planet and sun for quite a while, but I need you to be a bigger thinker than that. It's an object orbiting a gravity well, right? So when I say it like that, I mean it could be a satellite orbiting the Earth. It could be a moon orbiting a planet. It could be a planet orbiting a star. It could be a star orbiting the center of the Milky Way. All of these things are in orbit and all share the same characteristics. So whether we're talking about the space station, or we're talking about our moon, or we're talking about the Earth around the sun, all of these things are in orbit. And all orbits share the following characteristics. The general shape of an orbit is elliptical. And my understanding of your knowledge here has led me to have to say a few things. First, an ellipse is measured by its eccentricity. Have you heard that phrase before? The eccentricity of an ellipse is a ratio of the semi-minor axis to the semi-major axis, the short side to the long side, which means all ellipses have an eccentricity that is 1 or less, because it's always the small side to the large size. The smaller the eccentricity, the more skewed your ellipse is. Now, you're supposed to know more about this. For example, you're supposed to know that an ellipse has 2 foci. Right? Have you done this yet? It's supposed to be part of your, this is pre-calc, I'm pretty sure. The separation distance between the foci becomes more extreme when you have a more eccentric ellipse. Kepler's law states that all orbits are elliptical. Bless you. All orbits are elliptical, and that the star or the planet or whatever is the center is located at one of the foci. So if it's the Earth-Moon system, the Earth is located at one of the foci of the ellipse, and the moon is orbiting in such a way that it gets closer to the planet at some points and farther away at other points. Now, most inner planets have nearly circular orbits, and a circle is a type of ellipse, just like a square is a type of rectangle. But earlier today, when I asked this of my students, they were unsure. So let me make it perfectly clear. A circle is an ellipse that has an eccentricity of 1. Because no matter what 2 diameters you take, they're the same size. It also means that there aren't 2 foci, but 1 center, and the foci overlap at the center. So a circular orbit is special and is a subset of all orbits. So when Kepler said that all orbits were elliptical, he was still referring to orbits that were circular. Now, elliptical orbits are difficult for us to study mathematically. And I think you would probably be able to figure out why if you would just kind of consider the nature of a ellipse and what's going to happen as the planet or whatever, the thing that's orbiting, goes around the sun. So let me get rid of the axes because I don't need them. Got rid of the wrong thing there. There. Imagine the 3 locations I've kind of indicated for our orbiting object. And let's go ahead and say planet at center and moon going around the outside. Is that okay? So is it clear to you that the separation distance is greater here, so the force is going to be the smallest at that point? And is it also clear to you that it's closest here, so the force is going to be greatest at this point? And somewhere in the middle, that all makes sense? Now, remember, at any time, a planet is going to have a velocity that is tangent to the curve. Or the moon is going to have a velocity that is tangent to this curve. The force from the planet does two things. It either speeds up the velocity of the planet and changes the direction of the planet. So currently, as the moon goes from stage 1 to stage 2, the force from the planet is causing the moon to slow down and change direction. Can you see that from the direction of the force relative to the velocity? When it reaches this point, it's kind of a bit of equilibrium, isn't it? It's not really an equilibrium position, but for that instant, the force is right down the line there. It's not speeding it up or slowing it down. That suggests that at 2, it's at its slowest. On the other side of that, again, velocity is tangent to the curve. Force acting towards the center, towards the planet. That force is speeding up the moon, but again, causing it to change direction until eventually it makes it all the way to here, where it's traveling at its fastest, but now it's going to begin slowing down as it makes its way to the slowest portion. In all of this motion, there's an interplay going on. And although we'll talk more about elliptical orbits, this is the basic concept of an elliptical orbit. Now, these are hard for us to study mathematically, because if we study them using Newton's laws, one of the things we run into trouble with is that our forces here the acceleration is going to constantly be changing direction and size. And the acceleration depends on where the moon is around the ellipse. That makes for some hard math for us. We might be able to freeze it and talk about specific points, but for our math, the things that we have access to in our catalog of mathematics, we're probably only going to be able to talk mathematically about these two places when the force is perpendicular to the velocity. Unless we decide to focus our attention on circular orbits. If we focus our attention on circular orbits, we gain an advantage mathematically. The advantage is that if our orbit is circular, then first, the force acting on the object in orbit is going to be constant. It will be the same size force because the separation distance never changes. Second, because it's traveling in a circular path, we have math to back up what the acceleration must be for an object in orbit. So, for the time being, we're going to focus on circular orbits because we can do a good job of mathematically describing circular orbits. Now, for the next few moments, I'm going to use words very carefully. I'd like you to do the same. There are 3 things that you have to bring together to understand how to deal with orbits. The first is the force of gravity, m1, m2, g over r squared. The r squared in this formula is the separation distance. So I will clearly state separation distance when referring to this r. I will clearly state separation distance. This is the distance from the center of mass of one object to the center of mass of the other object. But we're traveling in a circular path, so at the same time, we're probably going to use the centripetal acceleration. And for today's discussion, we're talking about v squared over r. I am purposely writing a different r here because this is the radius of curvature. And the radius of curvature and the separation distance do not have to be the same. We're going to start out in systems where they are the same, but they do not have to be the same. Lastly, we're mostly interested in the period of these orbits. How long does it take something to go through orbit? When that question is asked, you have to remember something about how this system operates. And we did an example at the beginning of class yesterday to clue you in. Distance equals rate times time. Objects that are traveling in a circular path have to traverse a circumference. And how long it takes for them to do so will depend on how fast they are traveling. This velocity and this velocity are the same. This is still the radius of curvature that corresponds to this r. The separation distance may be the radius of curvature, or it may not. It'll depend on our situation. So, I want to practice, and I believe I've given you enough information based on yesterday and today for you to practice. I want you to tell me how long it takes the moon to go around the Earth. I'm going to give you some information. And the first thing I want to kind of do with that information is point to here. We're going to use that to figure out the centripetal acceleration. And we're probably going to sub in to the centripetal acceleration v squared over r. That way we can get that value for v and use that to figure out t for time. That's kind of the order of things. And I'm telling you the order ahead of time, but this m, does it refer to the Earth or the moon?
The Earth.
See how this is a good question, huh? Let's consider what we have here. M1, M2 represent the two objects. If we're talking about the Earth-Moon distance, we're talking about the Earth and Moon system, mass of the Earth will be at the center, mass of the Moon will be the thing around the outside edge. This is a result of Newton's second law. This m refers to the inertia of the object being accelerated. What's being accelerated, the Earth or the Moon? The Moon. That is the mass of the Moon. So when looking at this function, this will be the mass of the Earth, this will be the mass of the Moon, and this will be the mass of the Moon. So do we really need the mass of the Moon? Do you notice right away that it's going to cancel out? That should tell you something. All things in the same orbit at the same speed, because the m doesn't matter. We'll get to that later. You need information from me, right? Mass of the Earth, 5.96 times 10 to the 24th kilograms. You want what else? The Earth-Moon radius, the Earth-Moon separation distance, which 384 times 10 to the 6th meters. And we're going to do the example where the Earth is at the center of the orbit. So the Moon is orbiting the center of the Earth. That will allow these two things to be equal. If we say the Moon is orbiting the center of the Earth, those two things are equal. That's not exactly true. We're making a bit of a fib here. Now, take a minute, and I mean a minute, 60 seconds, and find out the period. I don't mean to be harsh here. Don't take long, but you're going to screw up because you can't handle big numbers in your calculator. The answer, 28 days. So I'm telling you the answer. You're going to get 28 days or something close to 28 days. If you don't, you've made a mistake. But understand something important. When you solve this, t is not in days. T will be in seconds because g is in seconds. Newtons meter squared per kilogram squared. Newtons is in seconds. You'll have to convert your answer to days. All right, hurry. Lunch is finally hitting you, and besides the fact that I'm shockingly condescending, you're just uninterested. But I want to, you were trying to solve for that. All right, you wanted t. And in order to do that, you needed v. So you had to put some things together. So since I have these in my head, I don't have to worry about leaving them there. I would have done this algebraically first because there are some advantages. So let's do some algebra. First, mass of Earth, mass of Moon, G over R squared, where R, lowercase r, is going to be the Earth-Moon distance and the radius. That's going to equal mass of Moon, V squared over R. Good so far? Now, the first thing you could do is solve this for V. And there's every reason to take a minute and do so, because this tells you the velocity of any orbit. How fast does your spaceship have to be traveling to be in that particular orbit? You should put in the radius of the Earth here. The radius of the Earth is 6.37 times 10 to the 6th meters. Put in the mass of the Earth. That tells you how fast every single rocket has to be launched in order to just make it to low Earth altitude and not crash back into the Earth. Once you get that number, you might begin to appreciate why it's so hard to launch rockets. Because that number, big, is the nicest way to put it. And they have to get there within 9 to 11 minutes of launch, or else they fall back into the ocean or into Europe or Africa. Yeah.
So you said that R that you replaced the AC with was a different R than...
I said it could be a different R.
But in this problem, it's...
This problem, we said that we're going to orbit the center of the Earth, so they're not. Now, what you could do, and I wrote this up here for a reason, it's good to know how to get to the velocity, but the velocity is an intermediate step, not the end itself. So instead, I'm going to go ahead and cancel out the one R. And for V, I'm going to put in 2 pi R over T squared. All right, canceled out the one R, put in the expression for the velocity. I can square this and cross multiply. And when I do, I'll get MEG T squared equals 4 pi squared R cubed. This is one of Kepler's 3 laws. It's a result of Newton's laws. Newton proved Kepler. Kepler's law stated that the orbital period of the planets squared was proportional to the orbital distance cubed. He found it mathematically on a graph. But Newton's laws predict it for circular orbits, and it holds for elliptical orbits. Now, I don't want to stop here because you were supposed to solve for the period. So if I solve this for the period, I get 2 pi times the square root of R cubed over MEG. Remember earlier this year when I said that objects that are oscillating will oscillate with their inertia here and restoring force there. Do you notice the 2 pi and the square root match up with all the other oscillators we had in class? This is an oscillator. In fact, if I just take 2 of those away and put them down here, you realize you get the force of gravity in the denominator and you get the moment of inertia in the numerator. That's what that is. In the same way that for a pendulum, the period equaled 2 pi as the root of L over G, where L represented the moment of inertia here, and G represented the gravity. So we get the same kind of thing here in talking about an object in orbit. That 2 pi is a sign to you that we're looking at something that is cyclic, that's happening over and over again. Going back to what was written, though. This will get you right to the period. And you got 27.44 days if you typed everything correctly. Okay, so if you're going to do the Earth around the sun, you want, what was that? Mass of the sun, 1.99 times 10 to the 30 kilograms. What else do you want? Radius? I don't know what you're talking about. I want the separation distance between the Earth and the sun. Sure. This is the average, 149.6 times 10 to the 9th meters. Now, I want just a period. That should be all you need. I'll slide this over a little bit to remind you of what we did. While you're working, somebody in third period asked why I don't just write this as 1.496 e to the 11th. And I do have a reason. I want you to think about something for just a minute, since you're smart people and can do two things at once. At least you say you can when you're on your phones, but we know you can't. The mind doesn't work that way. The radius of the Earth is 6.37 times 10 to the 6th meters. The Earth-Moon distance is 3.84 times 10 to the 8th meters. If I wrote those numbers like that, there's no way for you to easily compare these two things. But if I tell you that the Earth-Moon distance is 384 times 10 to the 6th meters, now you can just ignore this portion and make a direct comparison on the size of the Earth relative to the distance between the Earth and Moon. We often put the same times 10 to the at the end of numbers so we can make relative comparisons. All right, hurry up. Mistake. So now that you found that the Earth does take 365 days, 0.24 days to get around, and why there's a leap year, I want you to consider the big mistake you're making about the Earth and Moon. I know you have to pack up, and if you need to, do so. I'm going to still say it. The Moon doesn't revolve around the center of the Earth. This is the separation distance between the Earth and Moon, center to center. But as I said to you last unit, if you just throw something in the air, the object will revolve about its center of mass. The Earth and Moon revolve around their mutual center of mass, which is pretty close to the surface of the Earth. That makes this what we use for gravity. But this distance has to be used for AC, and 2 pi r equals VT. That's our job tomorrow.